All right, so we've been discussing entanglement, and this is, of course, a very broad subject. So we're only really touching superficially on it. So just to recap, an arbitrary pure state psi in given some fact, so we assume we have some factorization of the Hilbert space, and then an arbitrary pure state can always be expressed in terms of an orthonormal basis, a product basis. So using a notation that's consistent with previous lectures, we have that I should call this C. We're here as, I'm assuming as before, that these are orthonormal bases for HA and HB respectively. Now, if psi can be expressed as in the form omega cross sigma for some omega in HA and sigma in HB, then we say psi is unentangled or factorable or a product state. And then otherwise, we say it's entangled. So there's no kind of neutral zone between these two concepts. Otherwise, it is entangled. Okay, now let's talk about mixed states. Mixed state entanglement. Was there a subject I went through rapidly at the end of last lecture that I promised to review more carefully, or was that satisfactory? I don't recall. It's been a long weekend. Well, you guys can just raise a hand and let me know if there's something that you wanted me to address. Okay, so mixed state entanglement. So here, in general, a mixed state. So now, of course, I'm using this shorthand notation. So here we have some state rho, which is equal to psi psi, a projector onto the Hilbert space. And then I've written everything out in terms of just the ket for simplicity. Now here we're dealing with mixed states. We can't use that notational shortcut. So in general, if we have some state operator rho, it's a linear operator. Did I decide to use notation D for density operators? So it's a density operator on HA cross HB. So if we have a general state, so this is an arbitrary preparation procedure. So any box you can create, I can describe with this state operator. And we can always express it in terms of our orthonormal basis, and the expression is a little bit messier. We have L, K, L prime, and K prime. And then, so here this is a scalar, so there's no hat, so it's an expansion coefficient. And we have the outer products, AL prime cross BK prime. So that's a general expression. And of course, you can think of, if we think of rho in its matrix representation with respect to the basis AL and BK, then these correspond to matrix elements of that matrix. So in particular, rho L, L prime, K, K prime is equal to AL cross BK rho AL prime cross BK prime, which are the the matrix elements. So now here's how we define entanglement. We say for a general state, an arbitrary state rho is called separable, which is equivalent to unentangled. If and only if there exists a decomposition of the form so this is a probabilistic mixture also called a convex combination. So in particular, each PI is a probability. Well, not with, but this is equivalent to saying that the PIs satisfy, I'll just say where. Okay, where each P, for every I, PI is greater than or equal to 0, and the sum over I, PI is equal to 1. It's a little bit pedantic. I'm just making sure everyone's clear on the fact that this is a classical probabilistic mixture, hence the term mixed state, of uncorrelated states, of factorable states. So if there exists such a decomposition for any choices of rho I on A and B, then we call the state separable or unentangled. And if no such decomposition exists, then we say the state is entangled. Otherwise, it is entangled. Okay, so that's great. So, so here for a long time, I mean, this is the definition of entanglement. For a long time, entanglement was strictly understood as, the negation of being unentangled. But more recently, people have managed to show that entanglement is a positive quality in the sense that if your state is not separable, then there exist tasks, such as quantum teleportation, with which you can have a higher success probability if you have access to a state that has some entanglement.
Didn't we say on Friday or Thursday that given an arbitrary mixed state, we can't say for certain whether we can write it in this way?
Yes, that's correct.
So this definition, how helpful is it?
Well, it's helpful in one direction, but yeah, you're right. So this is the next topic, which is, well, there's a lot of things we can say here, so I've got to pace myself. But right, so there's a big open problem. So here, that's always exciting. So let me just say this, open problem. Okay, so if you guys can solve this, a major result, open problem. There is no general procedure for determining if you have some state rho. So I give you a matrix, and I tell you what basis that matrix corresponds to. And I say, OK, that's my preparation rho. Or I give you some algebraic description of it. And I say, does there exist such a decomposition? This is a hard problem, and we do not know the answer to it. OK? Given some operator rho, how can we determine if a decomposition of the form in the definition exists? Okay? So we have partial answers to this, which I'll tell you about right now. Okay, not right now. I'm going to tell you some other things first. So remarks, just to give you a better feel for conceptually what's going on. So the first remark is that if rho is pure, which is easy to check, right? Trace rho squared will tell you if it's pure or not. If rho is pure, then the von Neumann entropy S of rho A, which is always equal to S of rho B, will be greater than 0 if and only if rho is entangled. This is not true for mixed states. I think I gave an example last class. So if the overall state is mixed, then this criterion does not work for reasons I mentioned last class. I also want you to notice that if rho is pure, then there are observable correlations between systems A and B if and only if rho is entangled. Okay, so let me just tell you what I mean by a correlation. Okay, I haven't thought about this in a while. Let's hope I get it right. So basically, if we want to talk about a correlation, typically a correlation function, we have some observable, some observables A and B, and we define a correlation as the expectation of AB minus the expectation of A times the expectation of B. And there might be some normalization factor. Does anybody remember? Typically, maybe, maybe not. Doesn't matter anyways, so I'm going to talk to you not the degree of C, but whether it's 0. So now, so how do we calculate these things? So here, AB is defined to be, the trace of rho AB, and then A is just the trace of rho A tensor identity. So here I'm just measuring some property of A, and here I'm just measuring some property of B. So this is on identity on B, and this is identity on A. Okay, so you can see that if rho, let's assume rho is pure, all right? So if rho is pure, then that means we can express rho as an outer product, right? So if rho is pure and unentangled, then rho is equal to omega sigma, which I wrote, that's a weird way to write it. I should write it this way. And then you can immediately see, when you plug that into here, that this is going to reduce to a product of expectation values. Okay, that should be obvious. So clearly C, hence C will be 0 for any choice of A and B. So there's no correlations between the systems. So you can't have correlations without entanglement if the overall state is pure, which is something that's good to remember. Now, but clearly, if rho is mixed and separable, remember this notion of separable has nothing to do with separable Hilbert space. This is a property of state operators, not a property of the Hilbert space. If rho is mixed and separable, then it admits a decomposition of this form, and it can have classical correlations.
What do you mean by a classical correlation?
Well, this is a classical measure of correlations. So if I have a probability distribution, this basically means that my probability distribution over systems A and B, my joint probability is not a product. It's not a factorable, what's the word? It's not a product of the two probability distributions. So, sorry, this is a well-defined concept classically as well, just from classical statistical mechanics or classical probability theory. And it carries over to the quantum setting. So this is, yeah, so there's nothing really quantum going on here except for how we evaluate this expression. So I guess you can just remove the hats and it's a classical expression. Okay, so observable correlations, because remember, I mean, when we're in the lab, we have access to experimental outcomes. And this describes experimental outcomes. So experimentally, we can measure quantities like this. Now, it might be that I might choose some A and B, which exhibit no correlations. But then there might be some A prime and B prime, which do exhibit correlations. Right? So you can't infer from a single pair of variables that there's no correlations. You have to explore all possible observables, which is exhaustive and impossible in practice. But the point is, these statements are true that this is true for any choice, for every choice of A and B, of observable A and B. For some, and this is true for some choice, for some choices, I guess, of A and B. So the point is, once we have a mixed state, we can have classical correlations. We can have correlations between the objects which are not due to entanglement, just like classically we can have correlations between objects, right? The correlation between, it raining outside and the chance that, half the people that come in the building are wearing a rain jacket. There's some correlation there, right? So that's just the classical concept of correlation. We have two quantities which show a covariation over elements of the set, which is people in the building, and days of the week. Okay, so I don't know that I adequately motivated entanglement. I kind of launched right into it. I kind of assume that anybody who has a remote interest in physics has heard about entanglement and its relevance. But let me just highlight, maybe it's worth highlighting some of the reasons why entanglement is interesting. So entanglement is necessary to violate a Bell inequality which implies the impossibility of a non-local hidden variable model. Okay, so I think I'm pretty confident we're going to come back to this topic and discuss Bell inequalities in more detail. But let me just put that there as a motivation for now while we go through some of the mathematical properties of entanglement. So here the idea is, you've all probably heard this story, but let me tell it to you again because it's often told wrong. So basically, EPR, Einstein, Podolsky, and Rosen in 1935, Einstein was keen on understanding quantum mechanics as an incomplete theory, that quantum states had uncertainty and so on because of the fact that quantum states were insufficient to specify the true physical quantities underlying our observations. And so these true physical quantities got the term hidden variables, were called hidden variables eventually. And so Einstein's idea was to prove that his colleagues had to start thinking about hidden variable extensions of quantum mechanics. And the way that he did that, he had many different arguments for why people should start thinking about hidden variables. And the EPR argument was designed to show that if you assumed that there were no hidden variables, so you assumed the quantum state gave a complete specification of physical reality, then there was a conflict between that assumption and the predictions of quantum theory, when you also assume locality. So locality is basically the idea that physical events that are space-like separated, so I have two space-like separated events. I want the physical events here to be independent of anything that happens in the space-like separated region. So of course they can both have a common cause source of correlations, but there can't be any additional correlations due to events here depending on things that I choose to do over here. Or someone else, Alice and Bob, Alice's results can't depend on what Bob chooses if they're space-like separated, based on the assumption of no signaling and special relativity. So the original EPR argument was designed to show that we had to consider hidden variables. And that was 1935, and it was not ignored, but certainly ignored by the people that mattered, which is Einstein's colleagues, like von Neumann and Dirac and Bohr and these people. Schrodinger, by the way, was on Einstein's side, although people don't realize that. This famous quote by Schrodinger where he talks about Schrodinger's cat, right? You've all heard Schrodinger's cat story. And there's this famous quote where Schrodinger's like, suppose you have a cat penned up in a chamber, yada, yada, yada. Has anyone here not heard this story? Okay, good. So, you have the poor cat in this chamber, and it gets killed by some radioactive event, but then he says, Schrodinger's like, so the cat is left in a superposition of being both dead and alive. So people have taken this to mean that Schrodinger believed that physical superpositions existed. But there's this great irony in that if you look up his paper, the section that's quoted, there's a sentence immediately preceding it, actually in the same paragraph, in which he says, if you assume that quantum states are a complete description of physical reality, then you are led to absurd arguments like the following. And he gives this reductio ad absurdum argument, which now it's been associated with him without that initial caveat, which is unfortunate. But no, Schrodinger was definitely on the side of Einstein that we had to think about hidden variables to make sense of quantum mechanics. Yeah. Yeah, thank you. That's an important typo. Okay, there's another little funny anecdote about that, which is that, so Einstein and Schrodinger had this great correspondence where they were trying to figure out what was going on with quantum mechanics, and two, how to convince everybody else that there was a problem. Because everyone else was just ignoring this issue and happily kind of calculating away with quantum mechanics and saying crazy things. Anyways, so Einstein has a letter to Schrodinger in which he describes a situation, an interesting way to make the point. He goes, look, here's what we should tell people. Suppose you have a mouse trapped in a box, and there's some radioactive event which triggers the explosion of some dynamite in the box, and then the mouse is left in a superposition of being both alive and blown to bits. And then Schrodinger wrote a paper about the cat in the box being destroyed by a vial of cyanide. And so Schrodinger's cat is actually Einstein's mouse. And I guess Einstein wasn't too upset about this, because actually there's a letter from like the 50s or something where Einstein's writing to Schrodinger and talking about how he can't believe that no one else is worried about this, that they haven't succeeded in convincing the community. And he says, especially that ingenious argument you had about the cat in the box being blown to bits by dynamite. So he misrecalled the two metaphors. He mixed the metaphors and also gave credit to Schrodinger for his own idea, which was pretty funny. But I guess that's what happens when you get old. Anyways, so all right, so, and then there's another, there's so many ironies in this that show that there's some very strong psychological and sociological factors at play. So in particular, the story has kind of a surprising twist, which is then, so here, I'm not gonna write all that down, but EPR 1935 point to a conflict between locality and the assumption of completeness, which I take to be essentially equivalent to the denial of hidden variables. Okay, and you're welcome to read that paper. And then what Bell did, Bell, who was worried about these things, made a remarkable insight. Of course, this is probably, the greatest paper of the last century, the last half of the century, I would say. People have called it one of the most profound insights of science. Also, it was, I think, submitted in 1962, and he couldn't get it published for 2 years, which tells you how much you should worry about what the referees say when you submit papers. So Bell in 1964 showed the remarkable thing. He showed that that there exists a conflict between locality and the conjunction completeness or incompleteness. Okay, what do I mean by this? Bell said, well, let's assume there are hidden variables. Okay? Then he said, well, then there's still a conflict with an assumption of locality. So Einstein would not have liked this, right? Because he had this clever argument where he was trying to give evidence against a particular interpretation, but it turns out both flavors of interpretation, complete or incomplete. So incompleteness means there are hidden variables, and completeness means there are no hidden variables, describing our physical reality. So Bell said, well, actually, the conflict is, so the problem, you can't pick out the interpretation as the problem. So these guys, so Einstein, EPR concluded, given that conflict, we need hidden variables. We must consider hidden variables because the assumption of locality was sacrosanct. And then Bell showed that actually the problem lies with the assumption of locality. Which is very troubling. Now, the irony I want to tell you about is that many of our colleagues read Bell's theorem, where Bell says, suppose there are hidden variables, there's a conflict between locality and the assumption of hidden variables, to conclude that the hidden variable program itself is flawed because locality is sacrosanct. So they're totally unaware of the fact that there's also a conflict between the denial of hidden variables and locality. So, I mean, it's sad, but this is the way it's often presented, that Bell's theorem tells us that the hidden variables program is, untenable or unnatural. But the point is that Bell's argument really shows that, either choice you make of interpretation, whatever your intuition tells you is the right way to go, there's going to be a conflict with locality. Now, I should mention that, these very fantastic interpretations, like many worlds and so on, kind of get around these issues. They don't really fit into the Bell's paradigm of interpretation. So Bell lays out a clear paradigm of possible interpretations, and that set does not include things like many worlds, things like consistent histories, and so on. This isn't a course on foundations, so I don't want to keep getting into this, but I just want to say that this is not the complete set of hidden variable theories you can imagine, right? Not hidden variable, of interpretations you can imagine. There are other things like many worlds which essentially deny realism. They deny that there is some well-defined notion of an objective reality is somehow denied, which is even more problematic in my mind, but it's a very popular view amongst quantum scientists. Okay, so that's one line of motivation for entanglement being interesting. It's a necessary condition for achieving these incredible insights. And then another reason why entanglement is interesting is quantum information. And I've touched on this topic already, but entanglement is a resource for information theory. So things like quantum key distribution, and things like quantum teleportation, which we'll touch on at the end of the lecture, at the end of the lectures. Okay, so the point here is really just to say that there's lots of reasons to think that entanglement is interesting. Okay, and so now let's talk about some mathematics. Mathematical characterization. Oh, by the way, a lot of people will tell you that entanglement is a resource for quantum computing, but it appears that that's actually not the case. That's a recent set of insights show that.
So when you say resource, are you using that in the strict sense of a resource theory, or just?
Both, I think. I mean, really qualitatively, the concept is this. I give you a task. That task is to achieve some concrete goal, some operational goal, which can be measured in a concrete way. And then you show that if something helps you do better at that task than not having that thing, then it's a resource because it helps you. So things like quantum teleportation, quantum key distribution.
But you're not using it in the sense of something that can't be created by the free operations.
That's usually how you, then when you want to be more concrete about a resource theory, then you have to set down a set of principles, and generally the concept of a resource only makes sense if you impose some restriction, right? So if you allow me everything, then there's nothing that's a resource because I have everything. So entanglement is a resource in a context where the LOCC context. So we say, let's suppose the following restriction holds. Alice and Bob can communicate classically. They can share random numbers, but they can't exchange quantum states. They don't have a quantum channel to exchange quantum states. In other words, I can't send Alice, if I'm Bob, I cannot send Alice a system in some well-defined quantum state. I can only send classical bits of information. Then when I place that restriction on what Alice and Bob have access to, then I can say, well, now they want to achieve a certain task and they have some difficulty doing it, or here's how well they can do it. Now I say, now give them 1 bell pair. How much better can they do? Give them 10 bell pairs. How much better can they achieve at that task? So they're restricted to LOCC, but then we feed them entangled states and see, well, there's certain tasks they can do better at. And then there's this whole game of characterizing the efficiency with which they can do things.
What is LOCC?
Oh, I'm sorry. LOCC is how much interest is there in this topic? Because I could spend 5 minutes talking about it. Okay, good. So, so basically, the kind of modern approach to quantifying entanglement is based on the perspective of resource theories. And so in particular, we have that entanglement is a resource only under the LOCC restriction, which I'll define now.
It could be other restrictions, although it would also be a
Only under, okay, some restriction. For example, LOCC, because there's also this SLOCC and things like that, right? So LOCC, which means local operations. And classical communication. Okay, so what this means is, i.e., what LOCC means, parties can manipulate quantum states quantumly on their own factor space. Okay, so this is kind of a loose, this is a very loose definition, but the idea is that you have Alice and Bob, so you have HA tensor HB, and then the idea is, well, Alice can apply unitaries. So for example, Alice can apply a unitary of the form U cross identity. Okay, so this is a linear operator on HA cross HB. So this unitary acts locally on the degrees of freedom of system A, but she cannot, but not a unitary of the form U AB, element of the unitary group on HA cross HB. Sorry, I'm using some. Let's call this a linear operator. Obviously, it's a unitary operator, which defines the unitary group. The set of unitary operators is the unitary group acting on HA cross HB. We haven't talked about group theory, so let's not get into that. So it's just some linear operation. So this could include something that couples the two systems, the kind of thing that would actually create entanglement given product states. So if she can create entanglement for free, because she can kind of remotely control the system of Bob and her own system at the same time with unitary transformations, then obviously entanglement isn't a resource because she can just do it, right? So these are the LOCC restriction is these are considered the free operations. And anything that's not in your set of free operations is a candidate resource. It allows you to do things outside of the set of free operations. And so when you impose this restriction, then entanglement becomes a resource.
Is there a reason that you've specified that the operations are unitary, or could she apply any?
Yeah, it's anything. It's any CP map, but we haven't talked about CP maps yet. So this is just, that's why I'm trying to use EG instead of IE, because these are just examples of transformations to clarify the distinction. But yeah, I mean, Alice can do any unitary involving her half of the system and also operations that entangle her half with other degrees of freedom she has in her lab, right? So she can do more general things than this, but this is an example. But she definitely can't do things like this, where we take arbitrary operations acting on the factor on the combined spaces. And so, so I'm not going to summarize this paper, this reference I gave you last time on the resource theory point of view. So the resource theoretic considerations you can identify kind of useful concepts, like there's the entanglement of formation. There's the entanglement of distillation. And there's the entropy of entanglement. So the entropy of entanglement is exactly what we saw last class. The entropy of entanglement for some state rho of AB let me just actually give this a pure state. For some state psi is equal to the von Neumann entropy of the reduced state, which is the same for both factor spaces. And so basically, this is a distinguished measure. As I mentioned last class, I didn't give the best argument for this. This is a distinguished measure of entanglement for a couple of reasons. And I don't want to review those. It's a distinguished measure of entanglement, and also, there exist. And let me just say that there exist maximally entangled states. So for 2 qubits, that's the singlet. And in general, the maximally entangled states are of the form 1 over square root of d. Am I using capital D or lowercase d for my, or neither? Small d, okay. So this is d is my Hilbert space dimension. Okay. You guys like counting from 1 or 0? Okay, so the uniform superposition over some basis picks out the set of maximally entangled states. Now, the set of it's a set. It's not a particular state. I hope I use the plural here. Maximally entangled state. So the point is, if I have some state of this form, which is maximally entangled, and we can pick out maximally entangled states based on things like how good are states at certain tasks, like quantum teleportation, and we can also pick out maximally entangled states by appealing to the LOCC restriction. So the idea is that if the LOCC restriction and the other properties of entanglement in the resource theory point of view give a partial order of states. So in other words, if I have a state with entanglement and I have access to LOCC operations, then I should be able to create a state with less entanglement. So there's a partial order in the sense that given some state rho, can I convert it to sigma? And if you can convert rho to sigma using only LOCC operations, but you cannot convert sigma to rho using only LOCC operations, we have a notion of irreversibility, and that implies a partial order, and it's like suggests that rho is more entangled than sigma, because I can create sigma from rho under my restriction, but I cannot create rho from sigma. And then once you have that partial order, you can say, well, which state is on top of the heap? And basically it gives me other states, but I can't get it from those other states. And that suggests the notion of a maximally entangled state. And once you identify a maximally entangled state, you realize there's an equivalence class of maximally entangled states. And in particular, if I just do a local operation on psi plus, so you have things like entanglement monotones, and you say entanglement should not increase under LOCC operations. Well, I guess that's implicit. And in particular, we have that entanglement is invariant under local unitary transformations. So really, I'm just giving you a flavor of the kinds of things that come up and are interesting, and this isn't a comprehensive overview of entanglement. At IQC, there are entire courses on this subject. So really, you're just getting a superficial overview here. So what that means is that if psi plus, well, psi plus is maximally entangled. So let me just say any state phi obtained as UA cross UB acting on psi plus is also maximally entangled. Remind me, I'm going to ask you to prove this. Okay, so I want you to prove this. It's completely trivial, but just to make sure you understand how things work, I'm going to give you the tool you need to prove it in a moment. Okay, so that concludes my brief overview of resource theories. So let's talk about the mathematical characterization again. So mathematical characterization is, well, the entropy of entanglement is an important mathematical characterization, which is well motivated from a resource theory point of view. There's also, I don't think this is well motivated from a resource theory point of view, but it's a very convenient way to characterize entanglement. We have the Schmidt decomposition. This is actually a very useful mathematical tool. It's the tool you need to answer this question. So it's the following. Given any pure state there exist orthonormal bases AI and BI such that psi AB, am I getting too low? Okay, this will be continued here. So such that psi AB is equal to the sum over I lambda I AI cross BI, where the lambda I are non-negative satisfying their square summable to identity, to 1. So this is true for, obviously it's true for a product state where lambda I, right? So what's a product state? A product state means that psi is unentangled and there exists some state A1 and B1 so there's only one term in this sum if psi is a factorable state. If psi is not a factorable state, if it's not unentangled, if it's entangled, then there's going to be more than one term in this sum.
Is the sum going to the max or the min?
The min, thank you. So then we can say psi AB is entangled if and only if the Schmidt number is greater than 1. So the Schmidt number is the number of non-zero lambda I. So using the Schmidt decomposition, you can show that that's true.
The Schmidt number is independent of representation?
I said, well, I don't know what you mean by representation. I said there exists some particular choice of bases for which this decomposition exists. Maybe there's some degeneracy issues which makes this non-unique, but generally speaking, the Schmidt decomposition, the distribution of lambda i's, I believe, is unique.
Okay.
In fact, I don't have to say I believe. I can probably tell you it's definitely true. Yeah, that's the next step. Right. So the Schmidt decomposition tells us in particular that, so just remark that rho A, which is the trace over B of psi AB, is just equal to the sum over I of, how does it work? Lambda I squared AI. Okay, and similarly, rho B is equal to the sum over I lambda I squared BI. So if you can find the Schmidt decomposition, then you can easily calculate the reduced density matrices.
It would quite often be the other way around, though, wouldn't it?
Yes, I think so. I think so. In fact, I don't think I've ever had the occasion where I've found the Schmidt decomposition without knowing a priori what it is. So I don't know what the complexity is of that problem.
I mean, the easiest way to find it is to do this, and then to
Yeah. Well, there you go.
That only gives you lambda I squared and AI outer product.
No, that's okay because
then you can find B, and then you've got B.
because lambda i's are real and non-negative, so the square root is uniquely defined.
Okay, yeah. It gives you the square. It gives you the lambda I, but the AI and BI are only determined at most up to a phase.
Yeah, but there's no phases in the Schmidt decomposition. Oh, I see. Do you think the phases are absorbed in?
Right. Yeah. But the
Yeah, I'm not sure about that, but granted, I haven't done this before, so off the top of my head, it's not obvious.
You're always working on identifying states that are multiplied by a frequency.
Right. I mean, that just tells you a lot about the system, but in order to actually
All right, I'm going to have to erase, I'm afraid. I guess I'm going too fast today. It's kind of nice when I can give the whole lecture without erasing anything. Are there any other questions about any of this in the back?
Is it also true that for that kind of transformation where you just apply unitary to each of the states separately won't change the entanglement entropy of a state?
That's true. Okay, so now we'll get to this. What we do know, the pieces we do know about this open problem. So how do you find out, given some, I do tomography, which is a way to determine what the preparation procedure was, to identify the state operator, the density operator that describes a particular laboratory preparation of a system or a real-world preparation of a system. So you have this density operator. There's a way to identify what that density operator is. And the question is now, does that density operator contain entanglement? So the first thing you do is you check, well, is it a pure state? Calculate trace rule squared. If it's a pure state, then you can determine if it's entangled easily by calculating the von Neumann entropy or the entropy of entanglement of the reduced state. If it is not pure, then we have a challenge. Okay. So what do we know so far about it? So let me call this entanglement of mixed states. So assessing. Okay, so this problem has been solved in part. So for H A cross B equal to C2 cross C2 or C2 cross C3 or this I've never seen, but I've been told it's true by people I trust. Okay, so I've never seen this, but I believe it's also true. So I'll just put a little question mark. I think this is also the case. If you have an infinite dimensional Hilbert space and a two-level system, in all of these cases, we do have a definite way to determine if the state is entangled for an arbitrary mixed state. There exists a method to determine the presence of entanglement. Okay, so how does it work? It's called the PPT test, which is defined as positive partial transpose the credit goes to Perez, Asher Perez, and some subset of the Horodecki family. So it's also called the Perez-Horodecki criterion. So the Horodeckies are an interesting case. There's, I don't know, what are there, 5 of them now or 4? There's 4. So there's the dad, and he got into quantum information, and then he has 3 sons who also followed his footsteps in quantum information, and they're like a powerhouse in the field, powerhouse group. So they have lots of papers published with various combinations of them. I think this would have been the father, because this is an old result, so I assume it's the father. But so Perez-Horodecki. So the Perez-Horodecki criterion. Okay, so I'm going to tell you how it works, but not why it works. To know why it works, you have to know something about completely positive maps, which we'll hopefully touch on. So let me give a more precise statement of what I'm going to give you. So the PP test, the PPT criterion. I guess my R's look a lot like N's. The PPT criterion is a necessary condition for separability for all HA cross HB, and it is sufficient so it's necessary and sufficient only in these cases here. So C2 cross C2, C2 cross C3, and I think also C2 cross C infinity.
So is it definitely not sufficient in other cases, or is it just
Yes,
not
it's
being
definitely not sufficient. So we know as a fact that it misses cases in these other dimensions. So this is a little bit tedious, but we'll go through it. Yeah?
If it's true for C2 infinity, that implies that it's true for C2 cross C infinity. That implies that it's true for C2 cross Cn.
Well, if it was the case, then I'm misleading you. Yeah. No, I mean, I think it's logically possible for it to be true for C2 cross Cn and not C infinity, and not be true for C2 cross C4 or any other C2 cross Cn. You can't just interpolate. But maybe someone can check this for me. I mean, so we can just resolve this now in lecture if anyone has like Google handy. Okay, so how does the criterion work? Sorry?
According to quantity, it's 2 cross 2, 2 cross 3, 3 cross 2. No, 2 cross 3.
Huh. Okay, well, it's a good thing I've got question marks there then. Okay, how does it work? So, sorry, this will take, we'll finish in 2 minutes. This will take a couple minutes. All right, so we take, we have rho, which is an element of the density operators on HA cross HB. And then, okay, I don't know why my notation here is inconsistent with the rest, but rather than try and change my notation on the fly, I'll just stick with this notation. So we have a basis, which I call M, where M is an element of 1 all the way up to the dimension of HA. And we have a basis N, where n is a basis for HB. And so the index runs from 1 to the dimension of HB. I guess I'm calling this capital M. I'm calling this capital N. And then rho admits a matrix representation of the form rho 1, 1, rho 1, 2, rho 1, M, rho 2, 1, rho 2, 2, rho M1, rho MM, where this is not what you expect because each row in this is a matrix, where each row ij is an n by n matrix, right? So this is what happens when you do the matrix representation of a... Oh, I didn't cover matrix representations of mixed states over the product Hilbert space. Okay, it's pretty simple, but maybe it's worth reviewing how that works. So you remember we talked about, let me just recall. So if you have some state psi cross phi, and psi is a column vector, psi 1, all the way up to psi m, and phi is a column vector going from phi 1 to phi n, where here each psi I and phi j is an element of the complex numbers. So these are just complex coefficients. And then this is what we did last time. And then to construct the composite state, we chose an ordering convention in which the rightmost index varies most rapidly. So by convention, then, we said that this was equal to psi 1, phi 1, psi 1, phi 2, psi 1, phi 3, all the way down to psi 2, phi 1, and so on. So now we're going to do the same thing with matrices, right? So now if I have some matrix, if I have a state sigma cross tau, which is an element of linear operators on HA cross HB, and then sigma has a representation of the form sigma 1, 1, all the way up to sigma 1 m, sigma m1, sigma mm, and tau has a representation, let's call it density operators. Tau has a representation of the form, this is actually true for arbitrary linear operators, let me just change that back. Tau 1, 1 goes to tau 1 n, tau n1, tau nn. Then my joint state, sigma cross tau, is obtained by just taking each coefficient. So, okay, here I'll be a mathematician and be pedantic and remind you that each of these coefficients is a complex number, right? Then the representation of this is of the form sigma 1, 1 times the full matrix tau, and then sigma 1, 2 times the full matrix here, and so on, all the way up to sigma 1 m. Okay, and you repeat the pattern. And then what you get is a huge matrix of the form sigma 1, 1, tau 1, 1, sigma 1, 1, tau 1, 2, and so on, all the way up to sigma 1, 2, tau 1, 1. And I think the pattern should be clear. And this goes all the way up to sigma 1 m tau 1 n. And then here the next row is sigma 1, 1 tau 2, 1, sigma 1, 1 tau 2, 2, and so on. Right? So it's just whatever I get by take sigma 1, 1, multiply it by each element of this matrix, and then we get a submatrix here within our larger matrix where all we have are sigma 1, 1s, and this is tau n1, and this goes to sigma 1, 1 tau n. So we have a submatrix, and then the next submatrix has all the sigma 2, 1s. Then we have sigma 2, 1, tau 1, 1, sigma 2, 1, tau 1, 2, and so on. Is the pattern clear? Okay, good. So that's how you construct this huge matrix, and this huge matrix is some mn by mn dimensional matrix. Okay? So that's how we construct the matrix representation of a composite system, of an arbitrary mixed state. Now, of course, this is a separable mixed state, but the principle holds, right? We can just write a basis of linear operators and do this for each basis and then add them all together with the appropriate coefficients. I hope that's clear. Maybe that's something worth reviewing in the tutorial if it's not clear for some people. Okay, so now what we did here is I'm calling each row 1, 1 here. So this is a slightly different notation than that. Here I'm just, this row, each element here is the n by n matrix. So I'm calling row 1, 1 this whole matrix. I'm calling this row 1, 1 in this notation. So as you can guess from the name partial transpose, the transpose is when you take a matrix and you transpose the off diagonals, right? You all know what a transpose is. So the partial transpose is that we're only going to transpose one of the two systems in our matrix representation. All right, so it's a bit of an odd or esoteric operation. So given this picture, then we say rho, we take rho and we apply the operation identity times t to rho. So next step, where t is the transpose. So actually what I probably should have done is just told you this first, okay? And then the matrix representation of what's happening is something you can all figure out in quiet time, right? But basically, we're applying a partial transpose, meaning we're only transposing one of the two systems, and that has a matrix representation. The matrix representation of this is means that this matrix goes to, under identity cross T, so this is our matrix representation of rho, it goes to rho 1, 1 transpose, rho 1, 2 transpose, and so on, rho 2, 1 transpose, all the way down to rho m transpose. So we're just transposing each submatrix, but we're not transposing rho 1m with rho m1. Okay, so I think if you just think that through, it'll be pretty clear what's happening. So you do that to your state, which I'll just mention that is not a well-defined physical transformation. So this is a mathematical operation, which is not a valid physical transformation. And that's part of the key as to why this works. So then the point is, now we know how to do it. So the point is, if identity cross T acting on rho. So this gives us a new density operator. Let's call it omega. If this matrix is positive, if it's a positive matrix, then rho is said to be PPT, is called PPT. It has positive partial transpose. Yeah.
By positive, do you mean the same thing, only defined rho? Like it's,
Yeah, by positive, I mean non-negative, which is,
all its eigenvalues are.
yeah, which is annoying because the correct term is non-negative, but physicists always say positive. And in fact, the thing is named after the incorrect term, so we're stuck with it. But positive means non-negative. And if identity cross T of rho, which is, of course, we're just calling it omega, is negative. So here I'll just put an asterisk. Here, positive means non-negative. So it means that the eigenvalues are non-negative. So if this object is negative, meaning it has some negative eigenvalues, then rho is called NPT. And the upshot of this is that PPT, well, I already said it, I guess, is a necessary condition for separability of rho. And NPT equivalently, equivalently, NPT is a sufficient condition for entanglement, i.e., NPT implies rho is entangled. So NPT tells you for sure rho is entangled, but you also can get a null result in the sense that how does this work? So if you get negativity in the eigenvalues, you know for sure rho is entangled. If you do not see negativity in the eigenvalues, if the partially transposed state is positive, then it may or may not have been entangled. So it's a kind of the test didn't work. You get it. What's the correct way to say that? You get not a null result, but it's undecidable or something. Okay. So and then the point is that PPT. So if rho is PPT, then it may be either entangled or not. I'll put this board up in a second. Except for the Hilbert's, except if, we have these cases, these special cases. So for C2 cross C2 and C2 cross C3, in which case PPT is a sufficient condition for separability, then PPT implies separability. Sorry, I'm getting sloppy here. Separability. Let me put this up. All right, we've gone pretty badly over time, but let's take a minute to take some questions, and then we can wrap up. Is that even legible? Sorry about that. Does anyone want me, for one question can be, please read what you wrote. I'll accept that. Okay.
So can you not have both positive and negative eigenvalues? Is either PPT or MPT? Is that true?
Sorry, if you have any negative eigenvalues, it's called negative.
Oh, I see. Okay.
So yeah, that's just linear algebra. So you say that something's negative if it has at least one negative eigenvalue. Yes.
So I guess I'm a little surprised that you don't have to trace out over B, because it seems like the transpose might make the B reduced density matrix length unphysical, which is, I thought, sort of what you're asking.
Okay, I'm not sure where you're going with this, but let me just give you a hint about why this works. Oh, is it the reduced? Let me think. No, I think this is right. Okay, it's right as is. So the how does this work? So it's basically the transpose map is a positive map, meaning that it takes positive operators to positive operators. But it's not completely positive, which means that if I apply the transpose map to part of an entangled state, so complete positivity, which I'll give a more rigorous definition later, is the assumption that the map is not only positive when acting on a state operator in its domain, but that a map is positive if you take that map, you tensor it with the identity map acting on another system. And if an entangled state between your system of interest and that other system gets mapped to a positive state, or if an arbitrary state of the joint system gets mapped to a positive state, then we say that that map is completely positive. So in other words, even when it acts on part of an entangled state where you do nothing to the other part of the entangled state, if it correctly creates a valid density operator in that setting, we call it a completely positive map. So quantum operations, the most general thing you can do in the lab is a completely positive map. If you assume that you were allowed to do positive maps that weren't completely positive, that means I could act locally on part of an entangled system and create something that produced negative probabilities, which is empirically impossible. So that's why we require complete positivity as a condition for a valid transformation, that empirical fact. So the point is now, what Perez and Horodecki realized is, well, let's take a map that's positive but not completely positive, which the transpose is. So the transpose is a positive map that's not completely positive. And then the point is then we can look at how it acts on entangled states. And if it produces an invalid state, because it's positive, if the state was separable, then it would take that to a positive state. The only way a positive but not completely positive map can take a density operator to an invalid state is if that density operator had entanglement. So that's the insight they had. Okay?
Those property hold for the over transpose, partial transpose for 2 cross 1.
Yeah, it's symmetric. Anything else? Everyone's hungry? All right, great. Thanks for your attention.